These waves actually, according to the theory, should cover all frequencies from 10 to the minus 17 hertz, corresponding to wavelengths about the size of the universe, up to about 10 to the plus 8 hertz, corresponding to wavelengths of order a meter. Yeah?
Generally, you're going to be trying to match with waveforms, right? Do you have some idea of what these gravitational waves from the first second should look like? Do you know what to mention?
So they're going to form a stochastic background, and that means in this particular case, we will not have theoretical templates that we fold our data into, but instead we have to do a different kind of signal processing. And so we will study what techniques can be used to search for this kind of a stochastic background and to distinguish it from noise inside the detectors themselves. So the data analysis will be a rather different story here. The interesting thing in this case is going to be the spectrum of the waves and then the correlations in the waves. We will want to know, for example, whether these waves form a Gaussian random process or a non-Gaussian random process. And we will talk a little bit about theory of random processes and understand what those words mean later in the course. So these should cover all bands up to 10 to the 8th hertz. Beyond here, according to our understanding of the very early universe, there is no amplification, there is no significant interaction with inflation in the very early universe. The strength of the waves, standard inflation, the version of inflation that the establishment advocates these days, has a wave strength that we will compute, and we will see that it is perhaps large enough to be seen through anisotropies of the cosmic microwave background, in fact, quite likely large enough to be seen that way by looking at the anisotropies of the polarization of the background in the manner that Mark Kamienowski has proposed. It plunges as you go to higher frequencies, and above about 10 to the minus 16 hertz, it's a very flat spectrum according to conventional inflation theory. However, there are other theories of the very early universe. For example, the so-called pre-Big Bang model, which give different kinds of predictions from standard inflation. One of the problems with standard inflation is that it does not really take account of string theory. And so the pre-Big Bang model is a first rather crude attempt to see what superstring theory would do to these predictions. That first crude attempt that was pioneered by Gabriele Veneziano at CERN and colleagues, and Alessandro Buonanno, who's here, has worked on these models as well more recently. It predicts a spectrum that rises sharply at high frequencies, a slope of 3, but where it rises, whether it rises in the Lisa band, the LIGO band, or above the LIGO band, we don't know. Now, my own attitude about this is that these pre-Big Bang predictions are totally unreliable, but they're the best one can do today, including the effects of string theory. And they are a warning that standard inflationary predictions, which are very pessimistic, have a rather good chance of being quite wrong. What's your attitude about it, Alessandra? So you agree? Okay, thanks. The information carried by these waves, they will carry information about the physics of the Big Bang, about inflation, about the equation of state of the very early universe, the first 10 to the minus 15 or 10 to the minus 25 seconds of the universe. And how do you compute the waves from this process? You use cosmological perturbation theory, and ultimately, in dealing with what comes off of the Planck era itself, you have to use quantum gravity. Now, I will not talk about quantum gravity, but we will work out cosmological perturbation theory. This slide I did not intend to include. It was left over from some previous talk. Phase transitions in the very early universe. the cosmological phenomenology is that as the universe expanded, the fundamental forces decoupled from each other one after another as the temperature of the universe decreased. So initially, at very high temperatures, all the fundamental forces were the same. And then the electroweak force decoupled from the strong force. Then the electric force and the weak force decoupled from each other, gaining their own individual identities. At each decoupling, there would be a phase transition in the properties of the vacuums of these quantum fields associated with the fundamental forces. And those phase transitions, particularly if they're strongly first order, can lead to rather violent motions of material at the time of the phase transition and shortly thereafter. And those motions can produce strong gravitational waves. In particular, LISA, in fact, turns out to be at just the right frequency band to detect gravitational waves from the electroweak phase transition, which would have occurred, according to conventional theory, when the universe is about 10 to the minus 15 seconds old. And so LISA will look for the waves from the electroweak phase transition, and if it sees them, it will give us wonderful information about the era when the electric force and the weak force were gaining their individual identities in the very early universe. LIGO will probe any phase transition that might have occurred at age about 10 to the minus 25 seconds. There is I don't know of any phase transition that is thought to occur here, though that's fairly close to the point at which a phase transition associated with what's called Pesce-Quinn symmetry breaking would occur. And so there's some possibility that LIGO might be able to get at that phase transition. So the science of this source is we want to do high energy physics. So as you've seen, I described doing nuclear physics with gravitational waves through colliding neutron stars off black holes. Here one goes after high energy physics, and one goes after these various interesting cosmological effects in the very early universe that have been hypothesized, such as topological defects, which we will talk about. And finally, there was a fascinating colloquium given last spring by Craig Hogan from the University of Washington, in which he took the recent speculations about our universe being a three-dimensional defect evolving in time, so a four-dimensional space-time defect in a higher dimensional universe, a defect that the particle physicists like to call a brane. So our universe is a three-dimensional brane evolving in time in a higher dimensional universe. And according to these ideas about the so-called brane world scenarios, all the fundamental sources except gravity are confined to the brane, and gravity is confined to some distance less than or about 1 millimeter away from the brane in the higher dimensions, in all the higher dimensions.
1 millimeter is like what, 3 sizes of universes? Or?
Well, so presumably the space-time geometry in these higher dimensions is the spatial part is Euclidean. I'm talking now about what's going on at a particular moment of time. There's one time dimension that's common to the 3 space dimensions and to the additional, say, 7 space dimensions, or however many additional space dimensions there are. And the geometry then of the space at a particular moment of time, once you've picked a slicing of so you've picked out a time, the geometry is locally Euclidean. And so I'm just talking about the distance in a locally Euclidean, say, 7-dimensional space, or 10-dimensional space, going off away from a 3-dimensional surface. And so the idea is that gravity can reach out in those additional 7 dimensions, or however many more, to a distance that might be as large as a millimeter. It might be a lot smaller. Now, the idea then arises that different pieces of our brain couldn't communicate with each other in the very early universe. But as the universe expanded, they would come inside each other's horizons, and suddenly this piece and that piece would discover that the brain in between them is wrinkled. They didn't know it was wrinkled to begin with. And so suddenly then this wrinkled piece of brain that was born with some sort of random wrinkles in it, suddenly it discovers it's wrinkled and it begins to vibrate in the higher dimensions. The only thing that feels these vibrations in terms of fundamental forces is gravity, because gravity is the only thing that can reach out into the higher dimensions. And so gravity feels the vibrations, and in fact, in these models, the vibrational energy all gets converted into gravitational waves. And so there could be a strong gravitational wave background from this process in the very early universe. So we will go after this. Of course, this is a very crude theory at this point. But for example, if there were an equipartition of energy between the energy and the wrinkles to begin with, and the energy and other forms of energy, the waves that we would see would be so strong they would be easy for LIGO and LISA to detect. So here's an example, a far-fetched speculative example where the universe could be filled with a very strong background of gravitational waves that LIGO and LISA would see with great ease.
We'll keep us posted.
You read the literature. There are papers.
As we go through this course, LIGO is going to be turning on.
Yeah, right. But unfortunately, I think we will still, by June, LIGO will not be close to design sensitivity yet. I don't think. We'll see. But maybe Shanti. I think it's going to take more like a year to get to design sensitivity. Okay, so that's all I want to say about sources, but that was just by way of giving you at the beginning of the course an overview of the kinds of physics and astrophysical phenomenology, some of the data analysis issues, some of the issues of how do you compute gravitational wave generation that are going to be the key issues discussed in this course. So are there any questions? Okay, then I want to make a sharp turn then away from these issues of a very quick introduction to general relativity, or to those portions of general relativity that we're going to need in the course. So I suggest that those people who know general relativity reasonably well may want to leave now. You may want to come back on Wednesday. I will talk about, begin doing some gravitational wave theory then, though elementary gravitational wave theory. But I can see people here that I know should leave. And so let me invite you to leave. Okay.
The relativists say they might have to teach this someday.
Well, they won't all have to teach it someday.
What is Kip going to do? We're going to do all the
Thank you, John. At least one person who should leave is leaving. The rest of you are welcome to walk out as I lecture when you begin to realize how foolish you were to stick around. Okay. Okay, so the first thing I want to do is explain, give a simple argument, a little different from the argument I gave last week, for why Einstein chose to describe gravity in the language of space-time curvature. Okay. And so the argument goes as follows. Einstein said, well, this is a variant of what Einstein said, my variant of what Einstein said. He said, let's look at a freely falling object. And so we throw an object up and let it fall freely. And when you look at the trajectory that it makes, of course, it's a parabola. But we know we can take a more sophisticated point of view about that object. We can look at that object as it falls from the vantage point of an observer who himself is freely falling. That is, from the vantage point of an observer who is in a Lorentz frame, or at least a local Lorentz frame, in the vicinity of the falling object. And so I'm going to be such an observer. And that moved along in an absolutely straight line. Okay? And it was an absolutely straight line in a rather sophisticated sense, in the sense of the local Lorentz geometry of the inertial reference frame that I carried with myself. And so you didn't see it, but as I jumped, I was carrying with myself a lattice work of rods and clocks. Small enough that the inevitable space-time curvature that is present in this room doesn't affect it. It isn't noticeable. It's a little lattice work with clocks in it and rods of just the sort that are used in special relativity to define inertial coordinates or Lorentz coordinates, with the clock synchronized by Einstein's mechanism of sending a pulse out from here to there, bouncing it back, and setting the time of reflection here equal to the average of the emission and reception times back there. So you go through all the process that you go through in special relativity of defining an inertial reference frame, and that gives me a set of coordinates that I carried with me as I fell. And in those coordinates, x0 for time, x1, x2, x3 for space, or I might call them t, x, y, and z. In those coordinates, the trajectory of that particle was an absolutely straight line. dx alpha, d tau, where tau is proper time measured by a clock that the particle carries, that is a constant for alpha equals 0, 1, 2, 3. And so another way of saying this is that the forward velocity of the particle of the eraser as it fell and is seen in my inertial reference frame, the forward velocity is absolutely constant. So the whirl line is a absolutely straight line. So that's the first step in the argument. The second step is to say, now, let me follow the fall of a particle for a much greater distance. And so let me begin on the surface of the Earth. And I will stand here on the surface of the Earth. And I will throw two particles, two balls, two erasers, whatever, absolutely parallel to each other up into the air. And then I will watch them fall back down. And in order to make sure that nothing acts on them except gravity, I will remove the Earth's atmosphere. I will stop the Earth from spinning. And I will either make them out of, make this out of particles that do not interact with the material inside the Earth at all, or else I will drill holes in the Earth along the trajectories that I believe these particles are going to fall on, so they just fall through the holes, through vacuum in these holes. And so these particles then fall, and we know from Newton's point of view that the gravitational attraction is toward the center of the Earth. And so correspondingly, these particles that were initially moving absolutely parallel to each other, they will be drawn toward the center of the Earth. And they, in fact, their trajectories will cross somewhere slightly beyond the center of the Earth. But each trajectory is a straight line. That was Einstein's assertion. That's the prediction of special relativity. A straight line in what? A straight line is seen in local inertial reference frames anywhere along the trajectory's path. So each trajectory is a straight line. And these straight lines were initially absolutely parallel, and yet they cross if we follow them far enough. We know they cross because we understand what goes on in this case from Newton's point of view. Newton says gravity makes them cross, makes the trajectories cross. And so we need a corresponding statement as to what Einstein says. The analogy that leads us to that statement is to talk over here about a different problem on the surface of the Earth, to talk about straight lines on the surface of the Earth that are initially parallel. So I take the equator of the Earth, I take a great circle, which is the closest thing there is to a straight line on the curved surface of the Earth, a great circle going up from here and going up from there. They're initially parallel, and as I follow them, of course, they cross at the North Pole. And we know that the thing that causes the crossing of initially parallel curves on the surface of the Earth is curvature of the Earth's surface. Curvature of the manifold, the space in which these lines live, the Earth's surface. And so, similarly, Einstein asserts that the thing that causes these straight lines to cross is a curvature of space-time, a curvature of the manifold in which these particles move. And that's what causes the crossing of these trajectories. So when you compare Newton's description with Einstein's description, you see immediately that what Newton calls gravity must be the same thing as what Einstein calls space-time curvature. And so that's one way of seeing then Einstein's point of view, that gravity is space-time curvature, or gravity is one feature of, at least, is a better way to say it, is one feature of space-time curvature. And so what I'm going to want to do in the next half hour, and it may extend over into Wednesday, is to develop a mathematical description of just this process of the motion of these freely falling particles that get pulled by space-time curvature to cross. And I want to discuss just this same process, first from a Newtonian point of view, and then from a general relativistic point of view. Okay. So, let me begin Newtonian. So from a Newtonian point of view, if I redraw this same diagram, I have these two particles that are moving through space-time, getting pulled into a crossing trajectory, initially parallel. And I want to introduce a separation vector that reaches from the location of one of these particles to the location of the other one at some initial moment of time. And so that separation vector is shown here. And I will use for three-dimensional vectors in three-dimensional space, I'll use boldface, which I will denote by a squiggly underline, like that. So this is Xi, the Greek letter Xi, and it is the separation vector from these two, between these two particles. And I draw it in such a way that it in fact is perpendicular to both of these trajectories. These trajectories are initially parallel to each other. Then the first time rate of change of this separation vector is 0 because the trajectories are initially parallel to each other. That's a statement of parallel trajectories. The second time derivative of the separation vector is not going to be equal to 0. It's going to be equal to minus a tidal tensor. I'm going to talk about tensors in just a moment. This is a second-rank tensor. It is something that has two slots in it. And if I put C in the second slot, I wind up with a vector. And this is the tidal gravity tensor. So let me ask, how many people in the class have never seen an equation like this with a tensor that has two slots and you've stuck a vector into one of them? Raise your hands high. Okay. So this is what this is the definition of a tensor. A tensor is a linear function of vectors, and it has some number of slots. And if you put a vector into each of the slots, then you get out a real number that is linear in the vectors that you've put in the slots. If you leave one of the slots empty, what you get out is a vector instead of a real number. Okay. Now, there is a complete isomorphism between this equation and something that most of you have probably seen, which is a discussion of tensors in terms of indices. So if I want to go over and talk about this in terms of indices, I describe xi by xj, which is a j component of the vector xi. What this is xi dotted into the basis vector pointing in the j direction. I'm doing everything here in Euclidean space for the moment, and so this is a unit vector pointing in the j direction. It could be the x, the y, or the z directions. And if I just take the scalar product of my separation vector with this basis vector, I get out the component of xi. We know also that you can rewrite xi as being equal to xj ej with a sum over j. When I have repeated indices like this, I will assume a summation in Euclidean space, just two repeated indices. I will assume that the summation is there, and I won't write it explicitly. So this is the usual expansion of xi in terms of its components. Similarly, this tidal tensor, or tidal gravitational field, epsilon, it has two slots. If I put two basis vectors, ej and ek, into it, I get out a real number, and that real number is, well, this is really supposed to be a script e, not epsilon. Script e, j, k is this real number. And for example, if this were the basis vector pointing in the x direction, this were the basis vector pointing in the y direction, I would have e, x, y is the tensor e, with ex put in the first slot and ey put in the second slot. And so these ejk's actually form a matrix, but the matrix depends on the basis vectors that I happen to have introduced. In terms of this notation, I can also reconstruct E from ejk. So here's how I compute the components from the tensor. But I can also reconstruct the tensor as a linear function of vectors, a real valued linear function of vectors. I can reconstruct it by taking ejk, basis vector j, and something called the tensor product, basis vector k. And there's an implied sum over j and k, which I will leave out. So I have to tell you what a tensor product means. So a tensor product has the following meaning, that if I have a vector and I take the tensor product with some other vector, this thing has two slots. And if I put a third vector in here then, and a fourth vector in there, as soon as I've told you what the real number is that I get out, a real number that's linear in A and B, then I've defined this tensor. And that real number is A dotted into U. That's a real number multiplied by B dotted into V. So that's the definition of a tensor product. A tensor product B is something that you evaluate it. It has two slots. Stick a vector U in first slot, V in the second slot, and the real number you get out is the product of these two real numbers. Obviously, this is linear in A and it's linear in B. Question?
About a contraction.
Pardon?
Is it a contraction or is it actually an inner product?
So it's an inner product, but if I were to use a index notation, this inner product here would be AJ, UJ, and that's what the inner product would be in terms of components. So it's also a contraction in this sense that it's a contraction on these two indices. Okay.
It can also be thought of as an outer product, where you say you talk in terms of row or column vectors.
I forget precisely how an outer product is defined, but I think the answer is yes. Can somebody help me? I don't know language except my own language.
It's just where you have a column vectors multiplied by a row vector.
Yeah, okay.
An inner product is a row multiplied by
Okay. That is a variant of this, okay? Now, the mathematical structure that I'm going to use in this course is somewhat limited. When you have matrices, you have things that column matrices and you have row matrices. That's somewhat analogous to having bras and kets in quantum mechanics. You can take an inner product between a column matrix, a column vector and a row vector, and you get a real number. Just as you take a bra and a ket and fold them together and get a real number. When you have a metric present, that mathematics is present in the absence of a metric. You can do that. You don't need a metric in order to take an inner product between a bra and a ket. You don't need a metric to take an inner product between a row vector and a column vector. When you do have a metric present, you can simplify the notation and the language by getting rid of the bras, getting rid of the row vectors, and having only column vectors or having only kets. And I'm going to do that here. So in differential geometry, the analog of the bras is something called a one form. And the analog of the kets is something called a tangent vector, if you do the full-fledged differential geometry. But when you have a metric around, as we do in general relativity, there's a one-to-one mapping between the one forms and the tangent vectors. And I'm going to identify the one forms of the tangent vectors, and I will have only one kind of vector around. Okay, and this is just not to have to introduce a massive formalism when I can get by with a simpler formalism. Okay. Other questions? Okay. So coming back here, then I can expand the tidal tensor in terms of basis vectors in this manner, or I can construct the components of the tidal tensor using the basis vectors in that manner. So I can go back and forth between the abstract notation and the index notation. Okay. If I go to this equation here and I ask, what does this look like in index notation? So this is the fundamental equation of tidal gravity. It describes the relative acceleration of these two particles as they get pushed together by the tidal field produced by the Earth. The index notation version of this you can rather easily show as d squared cj dt squared is equal to minus ejk ck. And when I write it in that form, it probably feels familiar, or at least the notation is something that most people in the class will feel comfortable with. But what this is a component version in some basis of an abstract geometric relationship that is defined even in the absence of any coordinate system or any basis. And one of the things that I really like to push when I teach courses in physics, and not just relativity, classical mechanics or fluid mechanics, is there's a great deal of power in recognizing that we're really working with geometric objects, geometric relationships between geometric objects, and that no coordinates are needed in order to define them. So this is the Newtonian description of tidal gravity, but I want to carry it further. I want to derive a formula for the tidal tensor in terms of the Newtonian gravitational potential, which is already familiar to you. The tidal tensor is not familiar to you, but the Newtonian gravitational potential will be familiar to you. So in order to do that, I want to take, I guess I can do it over here. I'm going to take these whirl lines of these two particles, and this whirl line I'm going to call A, that's particle A, and this one over here will be B. And I want to talk first about the this whirl line or this trajectory of particle A and its equation of motion. So particle A has an equation of motion that says d squared xj dt squared, where xj is the coordinate, x, y, or z, is equal to minus the partial of the Newtonian gravitational potential with respect to xj. And this is, I evaluated at the location of particle A. So that's the standard equation of motion that says that the acceleration of particle A is minus the gradient of the Newtonian potential. Similarly, the acceleration of particle B is minus the gradient of the Newtonian potential evaluated at the location of particle B. But what I want is the second time derivative of their separation vector. But obviously the separation vector that I'm interested in, this separation vector C, is just the position of particle A minus the position of particle B. And so if I simply take the difference between these two equations, subtract the second equation from the first, I get an equation for the separation vector. So doing that, then I have d squared cj dt squared is equal to this minus that. This is a function, the gradient of phi evaluated at A minus the gradient of phi evaluated at B, and I can expand that in a Taylor series in the separation vector itself, and I'm going to keep just the first term in that Taylor series. So that difference is going to be then minus d squared, this double gradient, xj dxk. So I've differentiated with respect to xk, and then I multiply by the separation vector ck. So this is the equation of tidal gravity in the language of the Newtonian potential. And I compare it with my equation of tidal gravity in terms of the tidal tensor, and I can read off the components of the tidal tensor. And that tells me then, comparing these two, that tells me that the tidal tensor, ejk, is just the second partial derivative of the Newtonian potential. Yeah, question? Yeah.
I was just wondering what the convention is for super squared square sub.
Okay, so yes, I see that I have been very sloppy here. The components of the metric is, for those who are familiar with this, the components of the metric are the Kronecker delta. And whether an index is put up or down is a matter of my mood at the time. If I'm feeling happy, I may put it up. If I'm feeling sad, I may put it down. But for you, there should be no difference. Okay. Other questions? Okay. So that's the description of tidal gravity in Newton's language. Let me now go over and begin a discussion of the same thing in general relativity. Let me begin here. So in general relativity, the first thing I need to do, just a second, let me just think, yeah, okay. First thing I want to do is talk about the trajectory of a single particle. It could be particle A. Now instead of having particle A move through Euclidean space, I now want it to move through space-time. And so I'll draw diagrams in which time runs upward. So I have some time coordinate running upward and spatial coordinates running horizontally. And I have the trajectory of this particle is a trajectory that through space-time that might look like that. This is occurring in space-time, and although I have written down coordinates, I don't need to use coordinates to discuss this, because space-time is just made up of events. Each event is a particular location in space at a particular moment of time. It's made up of events. And so this whirl line of the particle I can write as p of tau. P is just that particular event at which the particle finds itself when the clock, the ideal clock that it carries with itself, measures tau. Where I presume from special relativity courses you are accustomed to the idea of an ideal clock. An ideal clock is the kind of a clock that the world's best clockmakers try to make. It's a clock that measures a version of time, a type of time that makes the laws of physics take the most simple form that they can. It's a clock that measures the kind of time that appears in Maxwell's equations and the other fundamental equations of physics. It's an ideal clock. So each particle carries an ideal clock with itself. It measures proper time tau, and the particle's whirl line is a location in space-time as a function of tau, but it can also be described equally well as x alpha of tau, where alpha now runs over 0 for time, 1, 2, 3 for space. So you can describe it either abstractly or in terms of coordinates. The particle has a tangent vector, which is its forward velocity u. And this forward velocity can be written abstractly as dp d tau, and by that what I mean is the limit as delta tau goes to 0 of p evaluated at tau plus delta tau minus p evaluated at tau divided by delta tau. And now I have something that is the difference between 2 points or 2 events. The difference between 2 events, if they're very close together, that's just a vector. And so this vector here is a vector that's obtained by taking 2 very nearby events on the whirl line, p at tau plus delta tau, p of tau, construct the arrow that reaches from one to the other, then divide by delta tau, which makes this arrow long, whereas it was originally very, very tiny. Now, because space-time is going to be curved, as we've argued, we have to try to understand the nature of this vector that we wind up with. And so let me talk about the analogous thing. If I were doing geometry on the surface of the Earth, so 2-dimensional geometry on the surface of the Earth, I have a curve on the surface of the Earth, which might be p of s, where s is distance along the curve. And I then construct a tangent vector u, which is dp ds, defined in this manner. And so you take 2 points that are very close to each other, you build a little arrow that reaches from one to the other. They're separated by some tiny delta s, and then you divide by the delta s, and this vector gets big. And then you've got the problem, if you don't think about it carefully, that this vector that you wind up with that is big, where does it go? How does it lay itself down on the surface of the sphere? And the answer is that it doesn't. The key thing about vectors and vector analysis and tensor analysis is the formalism is built to be absolutely linear. That's the nature of, linear algebra is what's going on in tensor analysis. If we lay this vector down on the surface of the sphere, it's going to be bending around in a nonlinear manner. This is a heuristic statement, but you can make it precise. And so if you want this to be vectors and tensors to be described by linear algebra, this vector has to live in a flat space where you can do everything linearly. What is that flat space? It's a space that is tangent to the surface of the Earth at this point where the vector lives. So there's a tangent space. It's tangent to the surface of the Earth at this point, and the vector lives in the tangent space. So this is a subtle but very important point that one has to really be clear in one's mind about, or one can get quite confused later on. And so similarly, this tangent vector lives not in space-time, it lives in a tangent space, this vector u, which is the 4 velocity. If we were doing special relativity, then space-time would be flat and we wouldn't have to worry about this. But in general relativity, where space-time is curved, you have to think about it in this language. And in fact, the first course in general relativity that I ever took was from Eugene Wigner at Princeton when I was a first-year graduate student. And he developed all of tensor analysis by embedding space-time in a higher dimensional flat space. And he actually did the embeddings. And he went awfully slowly, but it was a beautiful course. I mean, if you're going to carry along these embeddings all the way along, then it's going to go slowly. So that's there lurking in your mind behind this. Whenever you see a vector, it lives somewhere and it lives in the tangent space at that point. Okay, so here's the 4 velocity. And what we're interested in is then what I'm next interested in is describing the nature of this whirl line. And I want this to be the whirl line of a freely falling particle. And for a freely falling particle, we have asserted that this has to be a straight line through space-time. It's a straight line through curved space-time, so it's the analog of a great circle on the surface of the Earth. I've erased my surface of the Earth with a great circle, but it's the analog of a great circle on the surface of the Earth. It's the straightest curve that you can have in the curved space-time, the straightest line you can have in the curved space-time. What does it mean to be straight? Well, what it really means to be straight is that if you go from this point on the whirl line to the next point on the whirl line, and you look at the 4 velocity of the next point on the whirl line, the 4 velocity here and the 4 velocity there had better be parallel to each other. And that's not true of the curve I've drawn, so this isn't a straight line. On the surface of the Earth, if you look at a great circle, it does have the property that as you go up along it, this vector, that vector, that vector, as they are parallel to each other in the following sense, that this vector really sticks out of the manifold, but if you project it down, if you project down into the manifold and make a little piece of the curve by projecting down into the manifold, these vectors really are parallel to each other. So we will make this issue of being parallel more precise later. Another way to say it, parallelism, is that if you construct a local Euclidean coordinate system here, the tangent vector here and the tangent vector there have the same components in a local Euclidean coordinate system. That's what parallel means, is constancy of the components. Similarly, then over here in space-time, parallelism means constancy of the components of the vector u in a local Lorentz frame. So it only requires that the local Lorentz frame be able to cover both points. And we will see that because we're looking at how things change at first order, not second order, that in fact, to the necessary accuracy, you can cover both points with a single local Lorentz frame. This has to do with doing changes at first order. When we go to second order, that's not possible. But when we develop the formalism, we'll see at first order it is possible. Mathematically, the statement that this is a straight line we write is saying that the derivative of u along u is equal to 0. And I'll define this derivative of u along u on Wednesday, but I should quit now. So I'll continue this on Wednesday. I will get into gravitational wave theory, but not deep into it on Wednesday because I haven't gotten as far as I had hoped to today.